Thanks for the introduction, Mike. This work was done alongside my brilliant colleagues at CMU, Karan, who's sitting on stage right now. Karan, why don't you stand up and give... Karan did a lot of the heavy lifting on some of the aspects of this work, so he deserves some credit. Also with Mayank, Goel, and my advisor, Chris Harrison. So today, microphones can be found in a wide array of consumer electronics. From smart speakers to smartphones, tablets and TVs, and even watches. But despite sound being a rich signal, these devices don't utilize their microphones to understand what's going on around them. So if you listen carefully, there's lots of interesting events there, but we're not actually using. So for example, a smart speaker on a kitchen countertop does not know if a user is making coffee, or a smartwatch does not know if the user is vacuuming, or typing, or brushing their teeth. So in this work, we developed a real-time, sound-driven activity recognition system called Ubicoustics. And we leverage microphones in existing devices. So I'm just going to lower the volume a little bit. And our system can recognize events of interest from a single classifier, despite capturing no training data in that environment. In this talk, I'll describe our technique for tuning deep learning models, which requires lots of high-quality data for very specific activities. But before I get there, let's first quickly go through related work. There's lots of awesome work in this space, and I'm going to highlight the most important ones. So first, our sound event classification systems leveraging deep learning techniques. So Google's audio set, which is a taxonomy of audio events extracted from annotated YouTube videos. The next one is SoundNet from Antonio Torralba's group at MIT, which is also closely related. And Deep Ear is a related UbiComp system. It was basically one of the first to show the promise of deep neural nets for audio-based activity recognition. But also in the HCI domain, there's a lot of work here. So first by Warden Koji Yatani's work on body scope, where they use wearables basically on the body to detect proximate events via sound. And finally, our lab's previous work on synthetic sensors shows how multimodal sensing could enable rich contextual sensing in different places. If you guys remember from our previous work with synthetic sensors, we were able to do some of the activity recognition similar to what you've seen in the video that I showed you earlier. But there was a big limitation, which is training data. So in order for the system to work, users had to collect data in situ, which is a hassle. And the models themselves don't necessarily transfer over to other locations. So we ask ourselves, how do you get huge amounts of high-quality data without pushing that burden into the users? And can we design a system that could generalize across locations and devices? It turns out there's an answer. Professional sound effect libraries employed in the entertainment industry. And in the next few slides, I'm going to show you why this is important and what properties this has, and I'll explain why this is useful. So, why sound effects? Professional sound effects libraries have very interesting properties. So first, they're atomic. Oh, that's too loud. A sound labeled as, a telephone ringing is tightly segmented and contains only that sound. Next, clips are also pure. Generally recorded in professional studios and devoid of background noise and echoes, as they are meant to be composited into richer sound scenes. Third, sound effect libraries are diverse, containing hundreds of variations of the same sound effect. For example, here's one, another phone ringing. Did you guys hear that? And another one. And another one. And another one. And, no, I'll stop there. As you can see, there's lots of different variations. But not only sound effects have these properties, but sound itself has unique properties. So sound can be easily scaled, both in amplitude and in time. And then second, sounds can be easily transformed, projecting them into synthetic environments by altering their reverb and decay properties. So an effect can be made to sound like it's in a bathroom. I'll click. Or in a living room. And then finally, sounds are additive, allowing two or more effects to be trivially blended together. So we can make the same sound effect and combine it with background tracks, such as, a bustling market, an office, or a tranquil forest. So you've got all these different parameters you could use just by using sound effects. So these properties mean we can take a single sound effect and transmute it into hundreds of realistic variations, and then project those into hundreds of synthetic environments. This volume of data is perfect for training and tuning deep learning models, while still retaining the advantages of highly curated and well-labeled corpus. So how does this work? And how did we implement this? I'm going to go through that in detail. So there are 3 big steps here. First is what you've seen, data augmentation. Next is the signal processing aspect. And finally, the model training. And I'm going to quickly go through each one of them. So you've seen in the previous slides how different properties of sound effects and libraries affords different augmentation properties. So these are all in the paper, and this is a visualization of what that transmutation and projection looks like. But let's examine this middle one, the reverb, and I'm going to talk a little bit about that and how we did it. So we performed 10 reverb augmentations in our sounds, and we picked 6 presets from Adobe Audition, and then we made 4 reverbs ourselves, and I'm going to show you how we did it. So first you find a space, like an atrium, for example, and then take a speaker and microphone setup, like the one shown here. And then what you do is you capture the frequency response of this space. So you send a frequency sweep from the speakers, and then the microphone receives that. There's a whole art to this placement between microphones and speakers, but in this example, we just used a single microphone placed roughly, facing the speakers. So once you have that, you take that space, and then you go to another space, like a bathroom, or you go to another space, like a slightly bigger workshop, or a tiny office. And then once you have that, once you have this frequency response, you can then perform a deconvolution operation on that frequency response, which would result in an impulse function like the ones you've seen here. And once you have that impulse function, you can then apply that to any audio file that you have using a convolution process, and then you have your custom reverb applied to a specific sound effect. So it's a nicely evolved process, and you could use it in different scenarios where you want to mimic a specific environment. So that's the data augmentation part. And then we go to signal processing. It's a very straightforward process. So once you have your data, you basically extract FFTs and take the spectrogram of the MFCCs from those FFTs, giving you a 96 by 64 spectrogram patch. And what this does is it's really cool. Once you have this patch, you can then put that into a standard convolutional neural network. Which basically, it can be any convolutional-based neural network. This one we're using VGG16, but you could use other things like ResNet. And then what we did with VGG16 is we used data that was already pre-trained in 8 million YouTube videos. And then we fine-tuned that on top of our sound effects data. So you have this really nicely integrated system. And if there's a better architecture in the future, these sound patches can still be applied in those architectures. Okay, so let's show a live demo and see if things are working on my end. So I'm going to skip this screen, and I'm going to bring in this guy here. So here's a visualization of that spectrum. So here's me talking, and then you could see the data, basically the system detecting that I'm actually talking. So if I do things like, I'm typing. Should be able to see, you see the detection there that it's typing, and if I take my phone, should be able to hear that it's phone ringing. And in these examples, it was never trained in this location, and this was all trained using the sound effects data that I've shown you earlier. I think I brought a toothbrush with me, so let me try this. If it works, it's great. It didn't work, but it does for other things like like when you're coughing. Okay, toothbrush didn't work, but the other stuff worked. That's my live demo. Okay, let's skip that guy. Let's go back to the other screen. Okay, so, this was just my laptop, but you can, microphones are everywhere. So you can scale this up to like a smart speaker, and there's all these other events that you can detect too. Like a dryer or a smartwatch. Not a dryer. Here I'm detecting that I'm knocking, that a dog is barking, or when a cat is meowing. When you're in the kitchen and you're doing all these cutlery, when you're chopping, all these different sounds around. And these are not trained in that space. It's all sound effect libraries.
Oh, hi.
So when you're coughing or when a baby is crying. No baby was harmed in this video. Okay. So how well does our system work? Let's run through the evaluation setup that we did. I want to make sure I finish my presentation, so I'm just going to go through real quickly what the evaluation is. So we sought to answer key questions. What is the classifier accuracy? Does sound augmentation improve performance? What is the performance across different devices? And what is performance against human baselines? So I'm going to set up this study in lots of different layers. So first we selected location contexts in which everyday activities occur, like the kitchen, bathroom, entrance of a house, office, workshop, outdoors. Like we did 7. And across these contexts, we picked 30 classes, which you'll see in the next slides. And these 30 classes are those events that you would see in most of those different contexts. So once we have that, we built different data sets using our sound effect data for different augmentations, including a holdout test set. And we also gathered test data in the wild. So I'm going to explain that a little bit. So for that in the wild test data, we had 50 locations, 12 users, 7 device platforms. We got a laptop, a watch, a tablet, smart speaker, an IoT sensor, a phone in pocket, and a phone on a table. These are all simultaneously recording data when we did all these in the wild data collection. And finally, we set up human baselines for comparison. We recruited 600 participants, 100 in the lab and 500 crowdsourced. And these users performed sound identification tasks. These are the same sounds that the classifier is evaluated on for our 2 test sets. So that's the setup. So now let's talk about the results. Here's what the classes look like. You can see the signals are very distinctive. So let's talk about the results. So for accuracy, so for the different type of augmentations, both on the holdout and the in the wild data set, here are the results. Here we see that the best augmentation is when everything is combined. That's when you get the highest accuracies. Overall, per context models trained on the holdout set and tested on, trained on the fully augmented data and tested on the holdout set achieved an accuracy of 93.9% and 89.6% on the in the wild test. And when we tune our model only on the audio set data, which is just what the baseline Google data has, that was roughly only 70.6%. So this result shows that there's significant boost in accuracy when you tune with sound effects data. We ran an even harder test, so where we inject 20% of unknown sounds into the model. The model should ignore those unknown sounds. And here we have the performance and the holdout test. Let me skip that. Okay. So on that holdout set, the performance was about 80.4%. And then we do all these other things with the accuracy metrics for the in deep learning models. It's very non-deterministic. So in order to avoid checkpointing bias, you need a validation set and an actual test set. It turns out our in the wild test set is a very good way to measure the accuracy of that. And then we did the numbers, and the results are over here. It's about 80.4%, and more details on that are on the paper. And so finally, we also want to see what the accuracy across different contexts is. So here's a breakdown. We can go as high as 94%, for example, in a bedroom setting, but the lowest one was in the kitchen setting because there's lots of different sounds there that could be competing, like a dishwasher may not be too loud, for example. And as you can see in the human baselines, the results track really well with the human accuracies and our system accuracies. And then finally, here's a breakdown across devices. So this is a surprising result actually. So the smartwatch and the laptop had the highest accuracies, and we suspect that because the watch is the closest to the source of event, then it can have those high accuracies, and the laptop has superior microphones. Okay. So like all other approaches, our work has limitations. So let me quickly go through that. So first is, real world is rife with noisy data, but our current system can only detect the most prominent sound, not like the mixture of all the sounds within the microphone that is receiving. So in future work, we want to leverage sound effects to further have, multiple sound event detection. Also, the number of events we can support is limited, so we want to scale that up. Right now, it's only 30, but we want to scale that up because there are more events in the environment. And then finally, you want to tackle the 800-pound gorilla in the room, which is privacy. So the richness of sound is a double-edged sword. On one hand, it enables fine-grained sensing, but you can also have like sensitive audio data in there. So we envision our model being run locally on devices, so it never leaves the device. Everything should run in there. And we did an implementation real quickly on actually a Raspberry Pi running on an AIY kit, and Ubicoustics works on this. So everything can be done on the edge through this system. Okay, and finally, let me show you some fun stuff. Some example applications on what this capability can give you. Overall, we believe our work demonstrates promising approaches for robust context sensing. So for example, a smartwatch could monitor a greater array of health indicators just by detecting that you're coughing. And if you're coughing a lot more frequently, we can detect that. Computers could estimate your interruptibility. So based on the fine-grained knowledge of those contexts, you can then model a more fine-grained approach for interruptibility. IoT sensors could also track equipment utilization. So if you put this in a workshop, we can track which tools are running, and then we can monitor whether they need maintenance or not. And then you can also have, your phones can also have like context-driven applications on it. So for example, it will prompt you to, hey, make sure you wear your safety glasses. And then it's going to give you an RPM value for what that, device would be good for. And then finally, you can tell devices what events to listen for. So you can have a drag and drop approach. Here you want to listen for specific things. And then you can have an Alexa app that would follow you through a recipe. So it knows that you're chopping. So it can detect that chopping events are happening, and it knows when you stopped.
Now that you're done chopping, place Bing regions into the blender and liquefy.
And so it knows that, and so you do your thing, you put it in the blender, and it knows what a blender sound is. So it keeps tracks of that, and now you have this contextualized information.
Add hot chocolate and enjoy.
So it knows that you're done the blender. You put it in the microwave.
Alexa, can you notify me when the microwave is done?
I'll text you when the microwave is done.
So it also knows when the microwave is done because it has a very specific pattern. Okay, so what you just saw was Ubicoustics, a real-time, sound-driven activity recognition system, bringing us closer to this vision of plug-and-play, general-purpose sensing that works across devices and locations. Hold on, let's check up on that microwave.
The microwave is ready.
All right, there you go. Thank you all for your time, and now open the floor for questions.
I just want to say the toothbrush demo was working very well right before the talk. But of course,
he saw it.
but then this is actual real live demo on stage. Okay, so we have time for a couple questions.
Hi, awesome talk, Gierad. Just one quick question. I was wondering if you had experimented with any kind of really low overhead ways of fine-tuning the model for a very specific setting. Like, let's say your laptop up here for this demo. Is there something very short that you could have done, like maybe play back and record a single impulse function that would have maybe greatly increased the accuracy beyond what it currently is?
So I can explain to you what was going on with the laptop. So the MacBook Pro, when it's overheating, increases the fan. And so when the fan increases, that overpowers the signal. And so one way to fix that would be just to have either an external microphone that is at least free of that noise. But in regular environments, it's noisy. So what you can do too is record many background noise on top of your existing signals, so that they're more robust to these other types of noises.
Great, thanks.
Thanks.
Hi, my name is Jason, and I'm an undergraduate student from National Taiwan University. Thanks for the great talk.
Thank you.
I'm wondering there, you've mentioned that one of the advantage of using sound effect as training data is that they're additive,
yeah.
which means they are able to be added together. But you also mentioned that you use a VGG model to train this data for classification. Mm-hmm. And I'm wondering, how are you going to train the data when there are multiple sounds happening together? Because you are not able to train the model with a single data that has multiple labels.
So that's a great question. So I have a future work on solving that exact problem, which is because you have the sound effects data and they're atomic and they're clean, you can make your training process so that your input are mixed signals and then your output is just that one file that you are interested in, that one event. So let's say you can have a dog barking, that's your event of interest, but you can mix that with like Blender and microwave and all these other things, because you have your sound effects data, right? You mix that, and then your output would be just that dog barking. And so what your model is going to do is it's going to try to like basically decouple the dog sound across all those other sounds. So that's one way. And then you're just going to have multiple models for different events like dog or Blender or coughing, etc. So that's how you can make a more robust system, basically just targeting that very specific event of interest. And I think that's a good way to go.
I see. Thank you.
Yep.
We have time for one last question.
Yes.
Yeah, when you use Foley, these libraries, cinematic libraries, sometimes they use other objects to make
Foley, yeah.
It's a good point. During your model, you have a couple words to say about that, and also discrimination, like, in terms of discrimination.
So the question was, sound effects use Foley. So if you guys are familiar with Foley, what Foley is like fake sounds, basically. They make, I don't know, like crunching in the snow using like sacks of rice or something like that. So they approximate the sound. So luckily, the events of interest that we're looking at are rarely Foleyed. And the reason for that is it's a lot cheaper to just record these sounds than to like make Foley out of them. Because in the entertainment industry, you use Foley for like getting someone stabbed or like blood splattering and things like that. You use Foley for those things. But if you just want to record like a toilet flushing, it's much cheaper to just like turn on the toilet flushing. So we're pretty confident that the events of interest that we're investigating are rarely Foleyed. And we've verified this with actual professional sound effect library, sound effect professionals in the entertainment industry.
Let's thank Gierad for a great